Welcome to Forecast Accuracy Metrics in Python. In this lesson, we will explore how to measure how good a forecast is using Python. We will use real-world time series data, learn several accuracy metrics, and build up to a simple mini-project. Whether you want to predict sales or the weather, these tools will help you understand your predictions better. Let us get started. Running the cell now. First, we get our tools ready by importing libraries. Pandas is for data, NumPy is for math, and matplotlib is for charts. This tells Python to load useful code from other packages. Pandas handles tables, NumPy does fast math, and matplotlib makes graphs. This command quiets warning messages so they do not clutter our notebook. Pandas helps us work with table data easily. NumPy is great for calculations in lists and arrays. Matplotlib lets us quickly and clearly visualize our data. Running the cell now. Try running this cell to set up everything for next steps. What is forecast accuracy? Forecast accuracy tells us how close our predictions came to the real values. If you can measure it, you can improve it. We will use a real sales dataset for our examples. Running the cell now. Now, let us load a shampoo sales dataset from the internet using pandas. This is where we prepare our data. We specify the CSV file's web address. We use pandas to load the file from that address. This shows us how many rows and columns the data has. Here we look at the first few rows to get a sense of what the data looks like. Running the cell now. Check the columns and number of examples. Notice month and sales. We will use these next. Let us clean up the data a little. We rename columns and make sure sales are numbers. We give our columns helpful names. Now both columns are easy to access by name. We turn sales values into numbers, in case any are bad or missing. We drop rows with missing values to keep our data clean and reliable. Running the cell now. Sometimes real data needs some cleaning. Now ours is ready for analysis. Let us see how sales changed over time with a simple line plot. We want to visualize our sales data over the months. Here we set the size of our chart for easier viewing. This line draws the sales as a line chart, marking each month's value. The title explains what we are looking at. This labels the x-axis as month. Now the y-axis shows sales. Rotating labels helps make them readable. This adjusts the layout so nothing overlaps. Finally, we show the chart so we see trends and patterns in shampoo sales. Running the cell now. Notice if sales go up, down, or stay steady. Finding patterns is the first step in forecasting. Forecasting with a simple model. To measure forecast accuracy, we first need some predictions. For now, we will predict each month's sales as the previous month's actual value. This is called a naive forecast and is a common starting point. Running the cell now. Let us create our naive prediction. Each value is just the previous month's actual sales. First, we do a naive forecast by shifting sales down by one row. Now, we have a prediction column. Each month's guess is last month's real sales. We print out the first 10 rows to compare real sales and our simple prediction side by side. Running the cell now. Try matching the prediction and sales values yourself. This will help you understand how forecasting starts simply. Our first row has no prediction because there is no previous value, so we remove it. We remove any rows where we could not make a prediction to keep things lined up. This keeps our model honest by only using the data where predictions exist. Running the cell now. Great work! Next we will measure how well this naive prediction did. Introducing error metrics. Forecast error means how far off our predictions were. We will learn three main metrics today. MAE, a mean absolute error. RMSE, root mean squared error. MAPE, mean absolute percentage error. Running the cell now. Let us start by measuring MAE, or mean absolute error. We want to find the average distance between our predictions and the real sales each month. We use NumPy to subtract, take absolute value, and average it. This prints out the MAE value, cut to 2 decimal places for easy reading. Running the cell now. MAE is great for beginners because it is in the same units as the data. Lower values mean better forecasts. Now calculate RMSE. This metric is very common in competitions and takes especially big errors more seriously. We square the errors and average, which makes big mistakes stand out. Taking the square root brings the answer back to original units. Printing RMSE lets us compare directly to MAE, but it will usually be a little higher. Running the cell now. RMSE is helpful if you care more about catching large mistakes. Which feels bigger to you, MAE or RMSE here? MAPE tells us our average error as a percentage. This lets us compare different datasets easily. To get MAPE, we find out how big each error is compared to the true value, then average those percentages. Multiplying by 100 gives us a percent. Seeing the number as a percent helps set goals for future improvements. Running the cell now. Sometimes data has small or zero values, and MAPE can give extreme or undefined percentages. That is a limitation to know. Let us plot the errors over time. High spikes show where our model missed badly. We create a list of each month's error, making a new chart just for how far off we were each month. This line sets up the plot size. We draw the errors as a line, coloring them red for easy spotting. The chart title explains what we are seeing. Label the months. Label the error axis. Drawing a horizontal line at 0 helps see if we tend to be too high or too low. Rotating dates makes them readable. Fixes the layout to show everything cleanly. And finally, we show the chart. Watch for patterns of missed predictions. Running the cell now. Do errors trend positive, negative, or random? This helps spot bias and model improvement ideas. Measuring forecasts, quick recap. MAE, average size of our mistakes. RMSE, bigger mistakes matter more. MAPE, mistakes as a percent. Why do you think different jobs might care about one more than another? Running the cell now. Let us practice. Try to guess next month's sales, then see how close you got. We ask you to type a guess for the next month's sales. Now we reveal the real sales and ask you to retype your guess for practice. We work out how far off your guess was and show that error. Comparing your prediction to the truth is how accuracy is judged. Running the cell now. Practice, try a few guesses and see if error gets smaller each time. If you are finding this helpful, like and subscribe so you never miss an upcoming tutorial. Let us let you choose any 2 numbers to see how actual and predicted values build the error calculation. We ask for a prediction from you. Then we ask for the real outcome. Showing your absolute error is a quick way to see if you are getting closer. If actual sales is not 0, we work out how far off as a percent. This block adds an important check to avoid dividing by 0, which is always good practice. We show the percent error only when possible. If real sales were 0, percent error does not make sense, and we let you know. Error handling in code helps prevent crashes or confusing output. Running the cell now. Try experimenting with different numbers. Notice what happens as guesses get closer to real values. But is our naive model really better than just guessing? Let us test by comparing it to totally random predictions. We set the seed to make our random results repeatable. We make some random sales guesses between the smallest and biggest seen values. Now, we measure how far off those random guesses are using MAPE. We also check the naive shifting forecast from before. This line prints how far off random guessing was. This shows how well our simple model did. Usually, method beats guessing. Running the cell now. Did our shifting model beat random guessing? Almost always yes. Try inventing your own simple rules for forecasting as a challenge. Using built-in scoring functions. Libraries can calculate errors for you. We will use scikit-learn's tools. They work the same way, but save typing. Running the cell now. These built-in metrics do the same job as our homemade metrics. They are faster to type and less prone to mistakes. We import two standard error metrics from scikit-learn. This gives us MAE the official way. Next, we use the library to get mean squared error, then square root for RMSE. This line prints our library-based MAE. And here is the official RMSE. Let us check they match our earlier answers. This builds trust in both approaches. Running the cell now. Built-in functions are a good habit for bigger projects. They also handle more options and tricks later. Mini-project time. We will compare the naive shifting model to a new, slightly smarter model. It uses the average of the 2 preceding months to predict the next month. We create a mean forecasted column by taking the rolling average of 2 months, then shift for fair alignment. Again, we calculate the naive model's error as before. Now we find the error for our new 2-month mean forecast. Here is the error for the naive approach. And here is the error for the mean forecast. Lower error means the approach is more accurate. Running the cell now. Which model is best here? Invent your own rule for forecasting using other previous values for a challenge. Let us see the actual sales and both forecasts on one chart. Seeing all at once helps grasp models quickly. We make a bigger figure for clarity. Draw the real sales as circles. Add the naive model as a dashed line. Now show our 2-month mean model as a dotted line. Label the y-axis with sales. Label the months. Set a helpful chart title. Legend helps us tell which line is which. Turn month labels for readability. Tidy up the chart layout. Here is the final picture. Notice which model gets closer to the real data. Running the cell now. Try describing in your own words what the lines show. Visuals make numbers easier to understand. Today, data is not always perfect. What if sales data is missing or 0? Here we test if our metrics still work. We copy our clean data to a new table to not damage the real one. Set one sale to missing, nan. Force another sale to 0, which often breaks percentage calculations. Now try to calculate MAPE as before, inside a try except block, which is used to catch errors. If an error happens, print what went wrong. If it works, print the MAPE as usual. This block helps you see what real-world problems can pop up and how to handle or debug them. Running the cell now. Practice, try adding more missing values and notice what happens. Prepare your code for odd or bad data. Sometimes, a single weird value can ruin your metrics. These are called outliers. Let us find some with code. We find almost the smallest sales number. And almost the highest too, at the 99th percentile. Pick out rows where sales are extremely high or low. Announce any that are outliers. Print out the months and sales for these strange points. Seeing outliers helps you spot mistakes, data errors, or important events in time series. Running the cell now. Extra tip, try plotting the outliers on your earlier chart to see their effect. Challenge time. Can you invent another rule for forecasting using more months? Calculate MAE using just those forecast guesses. Try the whole lesson with a different dataset and see what changes. Share your ideas or results in the comments. Running the cell now. Recap what we learned. What forecast error means. How to calculate MAE, RMSE, and MAPE. Why real sales data is never perfect. Comparing simple and improved prediction models. Visualizing and troubleshooting errors. Great job! Running the cell now. Thanks for learning with us. Practice on your own, try different datasets, and experiment. If you like this lesson, hit like and subscribe so you never miss new tutorials. See you next time. Running the cell now.